Hello again. Tonight we're going to talk about Geminga or Geminga. It's a particular kind of pulsar, which is a rapidly spinning neutron star that is the remnants of a supernova. So, as I said, it's a rapidly spinning neutron star. It takes 0.237 seconds for one rotation, for one spin on its axis. It's the remnants of a supernova that occurred about 300,000 years ago. It's producing electromagnetic radiation, meaning photons. It's about 800 light years from Earth in the constellation of Gemini. And you can see down at the bottom right that picture of the constellation Gemini. And you can see the little red dotted rectangle that's down there in the bottom. You won't be able to see it in the sky because it's not producing light in the visible range. It is zipping across the sky at 472,000 miles an hour. So it's going horizontally across the sky. And that means that if you point your telescope at it every year, it'll move across the sky 178.2 thousandths of an arc second per year. So it's moving very slow from an individual's perspective, but very fast for something that far away moving across your field of view. There are other stars that move transverse across our field of view. The most noteworthy one is Barnard's star, which is just over 5 light years from Earth. And it moves about 10.3 arc seconds per year, not thousandths of an arc second, but 10 arc seconds. There's milliseconds, minutes, degrees. So while it's not moving anywhere near as fast as Barnard's star, it's still moving across at a pretty good clip. It was named Geminga by its discoverer in 1991, Giovanni Bignami. He passed away in 2017. It was a contraction of Gemini Gamma-ray and a transcription of Geminga, meaning it's not there. And you'll see the joke why. Geminga is in the Milanese dialect of the Lombard region of Italy, so it's kind of a flavor of Italian. Its name was officially given to it by the International Astronomical Union in 2022. It also has a catalog identifier of Pulsar J0633 plus 1746. Rolls trippingly off the tongue. It's also supernova number 437. And there is in gamma view of it in the Milky Way. And if you think of the center of the Milky Way, it's out off to one side, effectively not too far in angular separation from the Crab Nebula pulsar. So you can see it's fairly bright there in gamma. So what's odd about Geminga? It's not emitting in the visible portion of the spectrum at all. That's atypical for a high energy pulsar. So if you were to look out in the sky, even using the best optical telescope, there's nothing there. It's just dark. It's not emitting in radio. Most pulsars do emit at several different radio frequencies. In fact, that's how they found out about pulsars, is in radio. But if you point your radio telescope at Geminga, invisible, dark, nothing there. If you have an X-ray telescope, which you have to have it above the Earth's atmosphere because the Earth's atmosphere will stop the X-rays, it's dim, very dim. The image down at the bottom is in gamma rays, not X-rays. So it's at the low end, the what they call soft portion of the X-ray spectrum, and it's fairly dim. If you had a higher energy X-ray telescope, it wouldn't show up there either because it doesn't emit in hard X-rays, the higher end of X-rays. It's predominantly emitting in gamma ray. You can see there IC 443, the Crab Nebula, and Geminga. These are all bright in gamma. The bizarre thing is that this pulsar is traversing across the sky and nothing's going with it. It's not like moving with a nebular cloud. It's not like the center, not like a quasar, not the center of a galaxy. It's just all by itself cruising across the sky. Strange thing about that is most pulsars do have kind of a nebular cloud around them, and we can sometimes see in other spectra, other wavelengths, when the pulsar spits out radiation into the gas or dust cloud, it will brighten it in these other wavelengths, and then we can see where the pulsar is, even if we're not getting the beam from the pulsar directly, like the pulsar is turned on its side. So we're not actually getting the photons from the beam. But in this particular case, there's no cloud around it. The picture in the upper right-hand part of the slide, there's a red arrow pointing to where Geminga is. This is Chandra, which is closer to being a hard X-ray observatory, and the Spitzer Space Telescope, which is infrared. Why it shows at all is the gamma radiation from Geminga is hitting the gas and dust in the nearby part of space where it's zipping through. And it irradiates that gas and dust, which makes the gas and dust put out infrared. So Spitzer could see basically the wake. Think about a boat going through still water. It produces a wake from the force of the bow plowing through the water. Geminga does the same thing, but it's not from the force of the wake of it moving through. It's from the fact that as it zips through, it's spitting out a beacon of gamma radiation, which is irradiating the nearby gas and dust, causing it to produce infrared. So it leaves this bow wake of gamma radiation. Very interesting. So how do we actually observe this? Well, it's invisible in visual. It's invisible in radio. It's only indirectly visible in infrared. It's dimly visible in the soft portion of X-ray, best observed in gamma. The Earth's atmosphere is going to block much of the X-ray and gamma. If we had a satellite in orbit, we could see it either in X-ray or gamma. Orbiting out at L2, like where JWST is, would be even better. JWST is infrared. We could put another kind of telescope out there orbiting at a different orbital parameter that would be like gamma or soft X-ray. But we indirectly detected this pulsar. As it swept across, it produced a gamma ray burst, and it was detected by Cherenkov radiation. The observatory is called HAWC, and it's at high altitude in Mexico. And it's just a series of giant, very pure water tanks with very sensitive light detectors. As the gamma radiation interacted with particles in the upper atmosphere of the Earth that produce this very deep, bright blue light called Cherenkov radiation, and that radiation can be picked up as muons interact with the water molecules inside these water tanks and produce blue light. That's how we knew, as the pulsar comes around and spits gamma at us, we can see where the gamma is coming from. Strangely enough, this particular one pulsar produces about 20% of all gamma radiation hitting the Earth's atmosphere. So it's, in gamma, very bright. So if we went through and said, well, how did we look at this thing? The first instrument that NASA put up there called SAS-2, Small Astronomical Scope, number 2, first detected it. But it was just another thing in the background, and it was detected in X-ray. That particular telescope was deorbited or burned up in 1979. Then came NASA's Einstein Observatory. It detected it, also deorbited in 1982. Then the Rosat X-ray Observatory confirmed it as a pulsar because it was a better telescope and could see the X-ray beam like brightening and dimming. It was deorbited in 2011. The European Space Agency has their XMM Newton telescope. It's an X-ray telescope. It's due to be shut down for budgetary reasons in 2026, but won't have a replacement back up until 2035. So between when they shut it down in 2026 and hopefully when its replacement gets operational in 2035, the ESA will not have an X-ray space telescope. The US, NASA, does have an X-ray space telescope right now called Chandra. There's a picture of Chandra. It has been zeroed out in the 2026 NASA budget, even though it's operational, producing science, until that number is actually wrong. It should be 2035, not 2028. Once Chandra's turned off, maybe burned up, neither the US nor Europe will have an X-ray space telescope. XMM and Chandra do have a little bit of overlap capabilities, but they have different kinds of instruments that focus on different wavelengths of X-ray, soft, hard, and they have different fields of view, different amounts of sky they can see per image. And if you're wondering why the telescope kind of looks like it's backwards, the flap is on the near end towards us, the X-rays come in, and then the detector's all the way at the other end. That long tube is channeling or focusing the X-rays. And it typically focuses it with both dense pieces of metal and electromagnets, kind of like a dental X-ray. It has an X-ray emitter, and then they use magnets, electromagnets, to focus the X-ray beam. Well, they focus the X-ray telescope not too dissimilar way. But what if we wanted to look in gamma? NASA had a Jim Dandy gamma-ray telescope called Compton, deorbited in 1999. There is another NASA gamma-ray telescope called Fermi. It's still operational. So we can see it using Fermi, but not in X-ray after 2026. What about the indirect observing? Well, we used to be able to observe it indirectly via the Spitzer Space Telescope. That's an infrared telescope. It was put out of service in 2020. It's basically in a long orbit around the sun, but it was getting towards the end of its ability to have fuel left to successfully steer it where they wanted it to go. So they just basically switched it off in 2020. JWST, you can see it in infrared, and that's how they analyzed it recently. It's still operating good. But remember, if it's zipping through open space, going from like an area where there's gas, dust, and stars to an area of open space, you cannot see it except in gamma because there's nothing to illuminate. So in summary, in astronomical observations, if you only pay attention to visible, infrared, and radio, then you could be missing out on things that you can't see that are essentially invisible. High energy particle emissions, be they X-ray or gamma ray, you also need telescopes that can look at that. So I guess this is a roundabout way of saying, hey, Congress, NASA, don't defund Chandra. It's been up there since 1999. It's currently still operational, still producing scientific observations. At least leave it switched on until it's no longer operational or it runs out of its orbit management rocket fuel, or until NASA and or ESA successor X-ray telescope built, launched, placed into orbit, and operational, kind of like the U.S. does with its GOES weather satellites. Otherwise, for a number of years, the U.S. and the EU could be blind in the X-ray portion of the spectrum. And remember, this thing is putting out 20% of the gamma that hits the Earth's upper atmosphere. Not harmful, but let's say it was something much closer, a pulsar that only spits out in gamma. If we didn't have a satellite up there looking in gamma, we don't know what might affect us. So links. And then if you didn't know what Cherenkov radiation is, there are other Cherenkov radiation detection observatories. There's a big one worldwide that's going up as a multinational array. Comments? Questions?
Yeah, why doesn't the EU or some private science organization offer to buy that satellite for a pittance, since it's going to be decommissioned anyway?
Well, you can buy the satellite, but how do you talk to it? The only way it gets communication back with Earth is through NASA's Deep Space Network. So sure, you can buy the satellite from NASA, but how much do you think you're going to pay for communications time, given that the Deep Space Network is essentially overloaded at this point with all the probes they have up there? But I think, no, not never mind. I think you've got the right idea. With the advent of space creation corporations like SpaceX, Blue Origin, those kinds of things, I think that the technology and the rocket launch capability is sufficiently proven for Earth orbiting. As governments stop funding scientific research, much as they did for, other than spy satellites, orbital monitoring of Earth. The current budget is reducing the orbital monitoring because they don't want to hear the bad news about certain aspects of the climate, but they do for weather. So companies have taken it unto themselves to say, if I put a satellite up into orbit and it's looking in various spectra, I can maybe sell that data to large corporate farmers for an annual fee, and they can monitor their crops. They can see what parts of their fields are doing well versus what parts need, more water or more fertilizer or weeding. And that's a multi-million-dollar annual business. Not enough to cover the cost of the satellite in 1 year, but certainly with enough worldwide use, after maybe 5 or so years, they might be at the break-even point. I think the same thing holds true for scientific observations. Not that I would like private corporations to hold scientific observations as hostage, but if governments aren't going to fund the scientific research that many people realize is necessary, maybe private corporations that have some change in their pockets can develop the commercial satellites for doing X-ray observing, gamma-ray observing, maybe even radio observing, and then put those up in Earth orbit, put them up at geostationary orbit. They can see things as the Earth turns, and they don't have to worry so much about fuel for correcting trajectories, and they can stay up there for 100 years, as long as the electronics and the power and the solar panels work. So take science private and then charge for your observations. You can charge private corporations a different price than governments. If it costs $1 million a year to keep Chandra operational, charge the US government $800,000 a year. It's a bargain. And then, produce the gamma ray observations or X-ray observations that are needed to detect things. If you remember, they were going to remove some of the funding from the Rubin telescope in South America until the Department of Energy came in and said, hey guys, we use the Rubin to detect ICBM launches and detonations. So why don't we just give Rubin enough funding to bring it online and do its thing? But, don't worry about expanding it too much, but do our observations for us for the Department of Energy, rather than having the DOE work with NASA to put up additional satellites. We've got an Earth-based telescope. I think it's the science and the technology of space launches and satellites is more than sufficient to start taking this stuff private. And you want the data? We're not going to charge you a fortune for it, but we're certainly going to charge you enough that long-term we can cover our costs. So what do you think about that?
Really astonishing when you think about what percentage of the Earth is irradiated at any point in time by that one thing, that it would have 20% of the radiation. I mean, it's pointing at like what, a millionth of the Earth's atmosphere. I mean, you understand the sun. Per second. Remember, that thing spins on its axis every 0.2 of a second. So in 1 second, it sweeps past Earth times in a very short period of time. Even though it's 800 light years away, the gamma emissions are considerably powerful. But we have a nice atmosphere, Earth's magnetic field at the moment, so we're protected. But you said it accounts for 20% of the gamma radiation, didn't you?
Yes.
Yeah, for something that tiny and far away. I mean, Jesus.
Remember, one of the ways we early detected it as a gamma ray burst of Cherenkov radiation. So the Cherenkov radiation occurred in the upper atmosphere, and the muons that came down to the Earth penetrated these water tanks, caused Cherenkov, like deep blue light, to flicker, and the detectors picked it up. So yes, this is an enormous level of radiation. But if you have no gamma ray satellites, no X-ray satellites, you're blind to them.
Yeah, that isn't something that you'd like to have as a near neighbor. This was a very interesting talk tonight.
I thought it as, I saw this video. I saw, I hadn't heard of Geminga before. The guy that discovered it since passed away, but it was officially identified and named as something out there, as a cataloged pulsar. And it was kind of weird. I went into Stellarium and I just said, point at Geminga. It knew exactly what Geminga was. I went to Starry Night, which is more semi-professional, cost you money, and said, go look for Geminga. And it said, I don't know what you're talking about. I have nothing in my catalog's called Geminga. That's weird. So I went to Simbad by way of Starry Night, and Simbad could find Geminga, and it gave me all the alternative catalog names for it. And I found it in the Pulsar's catalog as PSR, that lovely identifier. That one Starry Night could find. because Starry Night has a Pulsar catalog, but they don't have the common name for it. So Starry Night didn't know it as Geminga. Starry Night knew it as PSRJ, whatever. But it's there. So yeah, what you can't see with human eyes or your most popular telescopes that see in infrared, they can still exist and they can still be producing a lot of radiation.
Yeah, if it was X-ray, we wouldn't need X-ray machines anymore. We could just position
Well,
people
no.
behind it with a X-ray camera.
The Earth's magnetic field and the atmosphere do attenuate X-rays, but this is down in the soft X-ray level, which, as you say, is kind of closer to the medical X-ray level. But I think of it more like, good thing we have the Earth's magnetic field and dense atmosphere. Otherwise, the X-rays would burn us up and the gamma rays would strip off whatever atmosphere there is, which...
and speaking of the Earth's magnetic field, did you see the Anton Petrov thing this week about the
Southern Anomaly?
Yeah. You may want to explain that a little bit for people who didn't see it, but to think that in the end, it winds up having a practical application that you need to turn off the Hubble Space Telescope whenever it passes overward. Did you know that? I bet you already knew that, didn't you?
Yes, I learned that. It's not just Hubble. I learned that several years ago. The interior of the Earth is a mixture of molten metal, molten rock, and some denser rock things that are a little closer to the surface, so they're not molten. And they get in the way of the molten stuff. As there's a section below South America that's a little denser, as the molten parts inside the Earth go swirling around, they kind of hit this denser part and go beneath it and then back up around it and swirl around this lump of rock around the bottom. It's like as if you took a sink and you had water draining out. So you had a Coriolis effect. You had the water swirling around. And then you took a small round bottom bowl, and while the water was draining down, you partially submerged the bowl into the water, and the water now had to swirl under the bowl and around. Same kind of thing, but with molten nickel, iron, and rock. As the magnetic field of the Earth is due to this swirling rotation of these metals, you get a magnetic field. That's what protects the Earth from the solar wind, particle radiation from space. As the material dips down below the hard lump, it causes the Earth's magnetic field to be weaker above that denser rocky area. And that happens to be in South America. Originally, it was just in South America, and now there's kind of a branch off that's out over the Atlantic Ocean that seems to be getting a little bigger. And when I was studying the Hubble Space Telescope in all of its infinite minutiae of its instruments and technology, in preparation for doing the same thing to learn about the James Webb Space Telescope prior to its launch, I discovered the South Atlantic Anomaly, or the SAA. And as Hubble is in low Earth orbit, it's going around the Earth about every 90 minutes. So if its orbit, because its orbit tilts over time, if its orbit's going to go over the core of the South Atlantic Anomaly, they don't want to fry the instruments, because as it goes over that area, the magnetic field dips, which allows space radiation to come down lower, and electronics can only take so much. So they didn't want it to be frying it. So if it goes into kind of a partial shutdown mode, if Hubble does that, they close the flap on the front. They partially power down a lot of the instruments. It's still communicating. It's still kind of on standby. And it zips over the SAA. And as soon as it gets past it, it can open up and start operating again until the next time it comes around. So as its orbit precesses over time, there are certain periods of certain orbits where it literally has to shut down, stop observing, and then open up and start observing again. So when you see these, boy, that deep space image must have a lot of image time on it. Yes, it's got 30 days worth of imaging time. No, it's not 30 continuous days, because the first problem is that thing's pointing out in space and Hubble goes around the Earth. So there's a period of time where Hubble could want to point at it, but it'd have to look through the Earth itself to see it because it's not moving in space and the Earth's rotating and Hubble's moving. So you can't see it most of the time. There's just windows where you can see it. But if you're going across the South Atlantic anomaly, you have to shut things down to avoid the electronics getting fried. And I thought it was kind of interesting that a non-US spacecraft cruising through the SAA actually had its electronics fried. So it's a real thing. But yes, I was aware of the SAA. But it is fascinating.
Yeah, he was saying that I think he was saying that astronauts who do spacewalks don't do it there either.
That's correct. You don't do spacewalks there. In fact, since there's a lot of gamma and high intensity X-ray, I would think that as astronauts in capsules are orbiting over the SAA, they can probably look out towards space and they can see flickering in their retinas because there's greater gamma radiation. That's something people maybe aren't aware of, but if you're an astronaut on board the ISS or in a capsule orbiting the Earth, at night when you want to go to sleep, you have these annoying little like fireflies that will pop into your retina, and that's literally a high energy X-ray or gamma particle, a photon that goes through your eyeballs, through your eyelids, into your eyeballs, and your retina gets excited and spits out a little light. Now, if you're facing towards the Earth, you may get fewer of them because the particles have to go through your brain, which has a lot of water in it. And water is a good mechanism for taking high energy particles and dampening them. If you're ever an astronaut in space and you want to go to sleep and you're facing out towards, away from Earth, and you're complaining about all the flickering, face down towards Earth and see if the flickering goes away. And then think about that for a moment.
Can't you get lead-lined nightshades or helmets?
Well, given how much lead weighs, you're probably not going to bring a lot of lead anything up into space.
Yeah.
But
speaking, I'm sorry, go on.
Osmium, you can probably get kind of an osmium foil and wear that inside of your, the communications helmets that they wear, the Snoopy helmet.
Yeah.
Probably get an osmium lined Snoopy helmet. Denser than lead, but you can make it into thinner sheets than lead.
Oh.
You know where I first learned about osmium?
No.
Boy Scouts.
Really?
How do you make your little down the slope racer made of wood go faster? You sneak
with tungsten?
No, you sneak a couple of pieces of osmium into the nose. Yeah, it's cheating. And they will find out about it because your car is supposed to be able to balance on the center of gravity. And if you've got lead or tungsten or osmium in the nose to make it go down faster, yeah, it won't balance. I know there was a whole South Park episode on it. So you like the topic, huh? An invisible gamma ray pulsar that's cruising laterally across our field of view while it goes sweep, 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 sweep with gamma rays.
Yeah, 20%. That's astounding.
20% of the total gamma rays. That includes the gamma from the sun. The sun, because it's an active star, doesn't produce as much gamma as explosions do or as pulsars do, but it produces kind of a different type of neutrino. Okay. Anything else before I stop recording? Hearing nothing.